From random number generators to tossing a coin, randomness is an interesting element of our lives. It plays an important role in many fields like computer science and probability, and is an essential part of scientific modeling. We hypothesized that if it's possible to predict randomness, we could calculate the chaos within certain objects. However, this introduced the question, can randomness really be predicted? We set out to find the answer. When flipping a coin, we use it as a way to settle something, because it is seemingly random. But there is no randomness in flipping a coin. If we knew the initial linear and angular momentum of the coin before being thrown, we could calculate exactly how the coin will land by using certain physics formulae. Therefore, flipping a coin is completely deterministic. Because of this, rather than being random, the more correct way to describe the randomness in flipping a coin is to call it a chaotic system. It is called a chaotic system because while it seems random, the only reason we can't calculate it is simply because we don't have all the information required to predict the results.
Another way we can visualize chaos, as mentioned before, is through the double pendulum. It's like your basic pendulum, but the only difference is a double pendulum has two joints of movement compared to one. This means we can produce an amazingly chaotic system that will work to help find the chaos needed for our experiment. We can start it in any position, give it a spin, and then it will start to do its own thing from there on. In order to better visualize the chaotic movement of the double pendulum, we can utilize a UV light and glow-in-the-dark paint to show the movement. To solve our question, we need to calculate randomness and chaos in two different ways. Chaos is completely deterministic, so if you know everything about the original characteristics, then you could predict what would happen in the future. Whereas randomness is completely unpredictable and you can never really fully determine what will happen to a certain thing in the future.
This is a double pendulum that we built. By using 3 1x2 boards, 2 radial bearings, 1 nut and 1 bolt, and 10 6-inch wood screws, we were able to build this double pendulum, which emulates a chaotic system. As seen here, if brought from any position, it shows a chaotic motion and is therefore a chaotic system. It helps emulate the double pendulum movement that we will see later in the MIT simulation.
A good example of a truly random system is that of an isotope's half-life. For example, with an element like uranium-238, we know that the half-life is approximately 4.5 billion years. So while we can predict almost exactly the number of atoms that will decay over time, we can't predict exactly when the delay will occur. Going back to the double pendulum, we realize that it's a chaotic system and is therefore predictable. Our purpose is to determine whether it is possible to predict randomness in a chaotic system by using a double pendulum.
Materials to build the double pendulum include 3 1x2 boards, 2 radial bearings, 1 2-inch spacer, 1 lag bolt, 1 nut, and 10 6-inch wood screws. Materials for the experiment include simply a computer and an internet connection. By using the double pendulum simulation designed by MIT, we can see the calculated movement of a double pendulum. Regardless of the starting position, the simulation is always able to calculate the movement of a double pendulum. Using several runs of the simulator while leaving space for variation, we were able to produce 4 very similar graphs which share the same patterns. As shown here, we can see the different X and Y patterns on each graph, which are identical if disregarding experimental errors to the path of the double pendulum from the starting point we chose. The simulation is able to calculate and output the movement of a double pendulum by using a relatively complicated array of formulas, ranging from kinematics to forces. From this, we were able to calculate the numerical solution and the motion equation by the position of the pendulum, the angle of the pendulum, the constant length of the arms, the tension on the arms, the mass of the pendulum, and the gravitational constant. Using all of this, the simulation adds all the variables into 2 final formulas, and then calculates it, which will result in the ability to quantify the chaos of the pendulum, and resultingly produces a state trajectory of a double pendulum. The use of the 2 formulas is due to the fact that unlike a standard pendulum, a double pendulum has 2 arms that both need calculations to be used in order to predict the movement of a total pendulum. So, in conclusion, W1, or the first formula, equals the angular velocity of the top arm. whereas W2, the second formula, equals the angular velocity of the bottom arm.
Firstly, using your computer, go to the MIT My Physics Lab Double Pendulum Simulator website. Secondly, once at the website, click on the Graph tab, which can be found at the top of the simulator. When you have reached the graph interface, you will see a graph where the x equals angle number 1 and the y equals angle number 2. This graph will be used for our data collection as it shows the predicted trajectory of the double pendulum. Thirdly, to collect the data, you will need to run the program several times from the same starting point to test whether the overall data that is being gathered is accurate, as well as to determine the specific pattern which can be seen through your results. Lastly, make sure each of the graphs has been recorded separately and that all the collected data from the simulator is clear of any previous collected data.
Finally, we can analyze our data and compare it to the movement of the double pendulum from the position we dropped it. Something we did was run the experiment several times to remove experimental flaws and increase the sample size. When looking at our data, we can see that when graphed, it follows the same movement of the double pendulum when it dropped from the same position of the pendulum that the data was collected from. This, therefore, proves that while a double pendulum is chaotic, as long as we know the starting characteristics and the position from which it starts, we can predict or calculate the exact trajectory and path it will follow.
In conclusion, we prove that the definition of randomness is one that serves mainly as an illusion, and that while most things seem random, they actually just follow a chaotic pattern. In terms of our double pendulum, we were able to discover if the starting characteristics are known, we can calculate the trajectory of the double pendulum accurately every time. Some experimental errors which we faced were that if not dropped from the exact point every time, there will be variations in the data, and during the multiple times we did it, we could see a slight deviation in this movement. Some possible improvements that could be made to our experiment are to find a simulator where the units of measurement for the pendulum arms are exact and specified, so we can build a real double pendulum to the exact standards of the simulation and compare their movement.